brought it to rest. That's because these currents were being induced in the conductors that acted like opposite magnets that slowed the thing down and brought it to rest. Okay? And so that kind of back EMF is something that you get in an inductor as well, because an inductor is just a whole bunch of turns of wire. And so because it resists the change, that means it takes energy to get current flowing through a conductor. And we'll discuss how much energy it takes in a little while. That there's going to be this resistance that you have to fight against. Now this is somewhat analogous to what happens if you try to charge a capacitor. Remember, when you're charging a capacitor, you build up charge and that produces a back EMF that opposes the change, because you're building up more and more charge, and so it keeps pushing back until finally you reach equilibrium when everything's at the same potential. Here, the source of it is different. That was just electric forces that were causing the back EMF. Here it's Faraday's law. The fact that we get a changing, the current's going through this way, then you've got a flux at any given moment that's going to be dA, and then you have a change in that flux, which is going to be dB dt times A. That B is proportional to I. Inside of a long coil, for example, B, we showed before, using Ampere's law, was mu 0 N over L times I. Okay, so that means that the magnetic field through the solenoid, through the long coil, B, is constant, and it's proportional to I. So as I increases, B increases. Okay, so we're getting, this is that form dB dt over a constant area. That's the form of Faraday's law that we're looking at here, because we've got a change in magnetic flux that's caused by a change in the magnetic field. As I goes up, B goes up. So that means that we've got a dB dt here. And that's something it has to fight against by pushing back in the opposite direction. Okay, so how do we define inductance then? Well, we can define it in terms of the following equation. And phi is the total flux through our inductor. I'm calling it an inductor, but it's some kind of a coil usually. Okay, so it's like a coil of wire. Long straight coil is the simplest kind of inductor, but I'll show you how to calculate the inductance for a toroidal coil in a little while as well. So n phi is proportional to the current, and that proportionality constant is L. So this is the proportionality constant between the total flux and the current. And as we'll see, the self-inductance, as was the case for the capacitance, is just a function of the geometry of the coils. Now, how does this help us by defining it this way? Well, where we're eventually going to go with this is we'll get the back EMF is going to be defined by d flux dt minus d flux dt. Okay, and so this is the total flux through n turns. So in other words, this is the flux through one turn. This is B, this is A, but then you got n of those. This is B, that's A. So you got n times the flux through one turn. I'll write that here, flux through one turn. Is proportional to the current. Why is it proportional to the current? Well, because B is proportional to the current for a long straight coil, right? The B is a constant value that's proportional to the current, and so therefore, whatever we've got in here for the flux is equal to B times area. Area isn't a function of the current. Okay? So that means that the inductance is just everything else that isn't the current in this expression. So if we do d flux dt, what that's going to give us then is minus L di dt. So this is what gives us our back EMF. So we do it, but if di dt is 0, then there's no back EMF. So it's just fine if the current is going through at a constant rate. But it's when the current starts to change that you get your back EMF that points in the opposite direction. So if the current's getting bigger this way, then the induced voltage, this is the back EMF, is going to tend to generate currents that move in the opposite direction. And so it's like a resistance term. And it acts very much like mass does. We talk about electromechanical analogies, and in a mass system, the energy is 1/2 mv squared. What we're going to show is that in a current-carrying inductor, the energy is 1/2 Li squared. And so there's an electromechanical analogy between the self-inductance because it acts like an inertia term that fights against the changes that produced it, just like inertia fights against changes in velocity. This fights against changes in current, which is also fighting against changes in velocity, right? Because the current is proportional to the drift velocity. So there is a real connection. It's not just a math relationship that doesn't have any physical significance. So anyway, let's go back here and let's find L for a long straight coil. Okay, so here then, we've got an area of each turn, and we've got n turns. And the area here is small. The square root of the area is much, much less than the length L of the coil. So that's our semi-infinite approximation. Say the radius is much less than L, or the square root of the area is much less than L. It's our semi-infinite approximation. And that's where this holds. We used, remember, Ampere's law to solve for this. Does everybody remember that? If you don't, you can go back to the notes, or if you took the notes, you take a look at it. We're assuming you know that. All right, so now let's find L. So that's going to be n phi over I. So what I'm expecting then is something that's just going to be a function of the geometry of the coil, and not something that has anything to do with current. The current should cancel out. Okay. So our flux then, in this case, our total flux, n phi, is equal to nVA. Everybody okay with that? If the number of turns of wire, n, and the flux through any given turn is BA. So we've got n of those, so it's NBA. And so n flux then is going to be NBA over I. But now we need to write the explicit dependence of the magnetic field for our long coil in terms of I. So this is going to be N times mu naught times N over L times I times A all over I. And so the i's are going to cancel, which is what we want. We don't want it to be a function of anything except for the geometry of the coils. Just like the capacitance, remember, was not a function of charge or voltage. It was just a function of the area of the plates and the separation between them. This is just something you pull off the shelf. It's got this value. And so that's going to be mu naught times n squared A over L, where L is the length of this coil. And so let's say here that the area is 1 square centimeter, that N is 1,000 turns, mu naught, 4 pi times 10 to the minus 7, Tesla meter per amp, and L, let's say, is 1 meter, just so we have easy numbers to plug in. That's a pretty long coil, but let's make it 1 meter. Okay, so here we plug in numbers, 4 pi, 10 to the minus 7, times 1,000 turns squared, times the area. Now we have to be careful with the area. We can't leave that in square centimeters. That has to be converted to square meters. So that's something that you would want to be conscious of if you're doing a problem like this. So the area then, 1 square centimeter times 1 squared meter squared for every 100 squared centimeter squared. Remember that you also square the conversion factor when you convert to square units. So this gives us 10 to the minus 4 square meters. And so we have to have this in units then that are consistent with the rest of the problem. And so that's going to be 10 to the minus 4 meters squared, all divided by 1 meter. Okay, so this is going to be 10 to the 3 squared, 10 to the 6 minus 4, that's 10 to the 2, times 10 to the minus 7, that's 10 to the minus 5. It's going to be 4 pi times 10 to the minus 5. That would be in units of Henry. I don't know why the units of Henry, but that's the units. Okay, and so what are those in terms of more basic units? Well, it's going to be Tesla meter squared per amp, right, from this expression. Because Tesla is the unit for magnetic field times meter squared. So that's units of flux is Tesla meter squared divided by amp is a Henry. And so if we want to punch out that number real quick here, it's going to be a certain number of millihenries, because 4 pi's are on 12, I think. So that's 12.6 times 10 to the minus 5 Henry, or 1.26 microhenry. Okay, so typically these values, even with a 1 meter long coil, are relatively small numbers of henries. Okay, that is the way that you would calculate it for a specific example, which is a commonly used inductance sort of a technique, is to just use a long straight coil. And so that's how we actually get a number out of it, and those are the units. Are there any questions about that? Okay, now we could have, and I gave you another example here in one of the handouts. which the flux varies, the little increments of flux vary over the extent of the coil. So for this example, let's figure out what the inductance is, not due to currents running through the coil itself, but from a current that's happening from a distance. So a current that's happening from a distance could also generate a voltage through this thing. And that sort of thing is what's called mutual inductance. Though we're not there yet, so don't worry about mutual. But just to get the self-inductance of it in this situation requires that we integrate the magnetic field over that area. So that's a little trickier than what we did earlier. Earlier, the magnetic field was constant over each area, and so all we had to do is plug and chug. It was just, what, NBA over, that was the total flux divided by the current, something like that. Right? That's all we did. So that's super easy for a long straight coil. But here the flux is equal to the integral of B dot dA. Okay, and so we're talking then about the flux in here due to a long straight wire. So that means that the magnetic field here in this side of this, we'll call this a square toroidal solenoid. Okay, so we're at that distance away, and we have n turns. Each one of them is a square of height h. Okay, and we are going to generate flux through this with a long straight wire that's somewhere else. And then if that current changed, we could figure out what the back EMF would be in that coil, because that would be a change in flux over that loop, and so that would just be L dI dt. Okay, so let's figure out what the flux is then, because once we have the flux, then n times the flux is equal to Li. So then we'll just have some expression that involves the current. We can cancel that out on both sides of the equation, and we can get the inductance of that square toroidal coil. Okay, so flux is the integral of B dot dA. Here, the magnetic field is different here than it is there. And in the middle, it's in between. Because the magnetic field in this long straight wire through that turn goes like mu0 I over 2 pi r. So the r is different. For each of these elements, the r is a different value. And that's why you've got to integrate the magnetic field over, that changing magnetic field over that area. So we can say that the little bit of area, we can do this in strips, because at any given value for the strip, the magnetic field is the same here. And at every value here along this strip, it's the same there. So we can say that this little bit of flux is equal to the magnetic field along that strip times a little bit of area, which is HDR. And then it's pointed in the same direction. The unit normal is in the same direction as the magnetic field, so it's times the cosine of 0 here. And then we integrate that, and so that's going to give us, for B, that's mu0 I over 2 pi r times h times dr. And so everything's a constant in there, except for the r, the dr and the r. So we pull all the other things, the mu0 I h over 2 pi outside of the integral, and we just integrate from a to b. Okay, so a then is this short distance, b is this longer distance. And so we do that, we get the log of r, evaluated from b to a. So we have the log of b minus the log of a. We evaluated those endpoints. It's log of b over a. Once we have that, then we can multiply, because this is just one term. We have n terms. So this could be actually a toroidal thing that goes around like this, where it has n turns, but all the geometry would be the same for every single one of those areas with respect to a radial magnetic field. So just very simply, we can take whatever that flux is and multiply it by n, set that equal to Li. So that's it. To get the self-inductance, what we need then is the flux, the number of turns, and then we just divide both sides through by the current. So that gives us mu0 n h, so that's here, without the the i's canceled, h over 2 pi times the log of b over a. The I is canceled out. And so that's our self-inductance for that kind of a toroidal, square toroidal coil. So that's a little more challenging, but it's another way that you could calculate inductance. Any questions about that? All right, well finally then, what I want to do is look at what happens if we think of this inductor as being another circuit element that's in a circuit. Okay, so we can have inductors, capacitors, and resistors in an AC circuit. And so what does the inductor do? Well, it stores magnetic energy, basically, in the magnetic field of the inductor. So what would that energy be? Here's the inductor. So let's say that we want to store some energy in that inductor. How can we figure out how to do that? Well, remember that it's going to fight against us. And so it means that we're fighting for the back EMF to prevent this from happening. So to build the current up, we've got to fight against that back EMF. And so that EMF looks like, well, N phi equals Li. And so N the flux dt is going to equal L di dt. And so this is going to be our induced voltage. Okay, this is what we have to fight against. This is our back EMF. Okay, and so what we could do then is say, well, power is equal to current I times voltage. And so the amount of power then is going to be equal to I times L di dt. But energy stored in the inductor as the current changes is going to be equal to the integral of power dt. So power is joules per second, and our stored energy, we can call that U if we want, is going to be the integral of power over time, because power is joules per second times the time. And so the power then is going to be L I di dt times dt. So that's going to be our stored energy in the inductor as we integrate. And so we've changed our integration variable then from time to current, because we can cancel out the dt's. So that just gives us Li di. Let's start with 0 and go to some current I. It's going to be Li di. And what's that equal to? It's just 1/2 Li squared. So this is the amount of energy required to get an inductor going with that amount of current. So this is stored energy, and we notice that this looks a lot like 1/2 mv squared. So that's the stored energy in a mass when you take a mass from 0 velocity and move it up to some final velocity. And so what's causing that mass to experience this resistance? It's this mysterious thing we call inertia. We don't exactly know what it is, but we know that the more mass something has, the more it resists changes in its motion. And so this is actually, in a way, less mysterious, even though it's less familiar to you. We know what's causing the resistance. It's, from Faraday's law, it's that back EMF that you have to fight against to build the current up to that value. And so you can think of this as being energy that's stored in the magnetic field. So what about when we have a capacitor? Well, the stored energy in a capacitor we showed before was 1/2 Q times delta V. Okay, and so where's that energy stored? Well, that energy is stored in an electric field. So we've got two kind of interesting expressions for stored energy, one for an inductor, one for a capacitor. And so something that we might ask then is, what happens if we put them together in a single circuit? Let's combine them. So our inductor is going to have this kind of a shape, just like a long coil, kind of natural for that. Capacitor is going to just be the symbol for two parallel plates. So here the energy, let's say we start out with an initial, I'm going to write it as Q squared over 2C. I'm going to have it be proportional to the charge squared. And here, when we have energy flowing through the inductor, that's going to look like 1/2 Li squared. So initially, at time equals 0, let's say the capacitor is fully charged. And then we close the switch, and we let it short out through the inductor. So time equals 0. We'll call this step 1 of the process. Charge capacitor switch over. And we close the switch. So at point 2 then, the capacitor, once we close the switch, is going to discharge. But where did the energy go? The energy went into the inductor. So at this point then, at point 1, the energy in the inductor is 0, because there's no current flowing through it yet. And by the way, this has an electromechanical analog to a spring. This could be like, let's assume that we've got a mass on a spring here, and it's pulled a distance x from equilibrium. Then at first there's no kinetic energy, and it's all potential energy at this point. But then we go to point 2, that's like releasing the mass, and then all the potential energy is gone when it reaches x equals 0. So now it's all kinetic energy, 1/2 mv squared. Whereas here, all of the energy is potential, 1/2 ka squared. But now the potential energy is 0. Here the kinetic is 1/2 mv squared. What is it here when we close the switch? Well, then capacitor is 0 at the point where it's completely discharged. And that energy has gone into building up the current through the inductor. And so it's not going to just give that energy up. It's not just going to suddenly go to 0 because it's not being driven anymore by the voltage across the capacitor. When it reaches that point, it has what we call inertia, because it doesn't like change. Just the same way as a mass doesn't like change, this current doesn't like change. And so it induces EMF that tries to prevent the change. And so at first, it's fighting against the current increasing, but then when the current's going to zero, then it fights against the decrease. Okay, so that's what carries it through, is it's fighting now because there's no driving force. The back currents are going to help drive it in the same direction, because that's the direction of decreasing current. So the eddy currents switch direction now. And now they're moving to drive this thing through that point. So it doesn't just instantly cause the current to drop to zero, but rather, it's like taking potential energy, turning it into kinetic energy, just like here. This is the electromechanical analog for what we call an LC circuit. And so it takes time then for this to go to conclusion. And so when we get to point 3, now the capacitor is all charged up on this side. The inductor has no energy. And so that corresponds to the mass spring system, where the mass is at its point of maximum compression. So this is some distance x equals a there. And the kinetic energy is 0, but the potential energy is 1/2 k a squared. So here, we've got the energy across the inductor is 0. What we have here, the energy across the capacitor is still q squared over 2c. But it has an opposite polarity, notice, to what we have over here. So it's completely charged, but on the other side. Because of all that inertia, drove that current through. The changes in flux kept it going until finally there's no current, but at that point the capacitor now is fully charged, but with the opposite polarity. So that's analogous here to the mass moving in the opposite direction and creating a compressed spring. And then it'll discharge again until we get to point 4. So at point 4, now the capacitor is completely discharged, and now the current's going through this way, through the inductor. So U is equal to 0, and L again, or U here, is 1/2 Li squared. Until finally, then, we go from 4 back to 1. And so here, this drives it until we get to this point, and we return to 1. And we complete the cycle. And then we continue the cycle. So basically, what this is doing then is this has created a clock. Because the amount of time that it takes to discharge and then recharge the capacitor is related to how much time it's taking for the current to switch energies between these 2 points. So at this point then, the electromechanical analog is it's back here at x equals 0, but now the velocity is moving in the other direction. In this situation, the velocity was moving this way when it got to this point. This is the velocity. It's going to the left when it was at x equals 0. Here, it's going to the right. And then when we get back to this position then, we'll go from 4 back to 1. Then that kinetic energy turns back into potential energy here, and we go back to repeat the cycle. Any questions about the basic concept before we do the math? Okay, so for a mass spring system, we've got F equals ma plus md squared x dt squared equals minus kx. So then the second derivative of x with respect to time squared equals minus k over m times x. We assume x is equal to a cosine omega t, and the second derivative of x is minus omega squared a cosine omega t. So we have here is minus omega squared a cosine omega t. equal to minus k over m times a cosine omega t. A cosine omega t's cancel, and we get omega is equal to the square root of k over m. So this relates then to the natural period of oscillation of our mass spring system. And so you might expect then that we would have some equivalent sort of mathematical expression, since it has what looks like the mathematical equivalent to what's going on with the mass spring system with its own natural period of motion. And this is what would make it turn it into a clock. It would have a natural resonant frequency. So our equation then, if we go around this thing, is going to be, well, the voltage drop across here is E minus what do we have here? Q over C minus L di dt would equal 0. Or L di dt, this is like MA here, F equals MA, derivative of velocity, but this is like mass, this is kind of like velocity, so MA equals minus Q over C. So we can write this then on the left as di dt is the second derivative of charge with respect to time squared equals minus Q over C. Or we can rewrite this as the second derivative of charge is equal to minus 1 over LC times Q. So all of a sudden now, this is looking an awful lot like this expression, but with my omega squared, instead of it being k over m, my omega squared here is 1 over LC. But we should get the same thing. If we assume Q is equal to Q max times the cosine of omega t, then the second derivative of Q with respect to time squared would be minus omega squared Q max cosine omega t. Remember, we're taking the derivative once, we get one factor of omega. We've done this before. Take the derivative second time, we get an omega squared. So we plug that into this expression, and we get omega minus omega squared Q max cosine omega t is equal to minus 1 over LC times the cosine of omega t. Gives us omega squared equals 1 over LC, or omega square root of 1 over LC. So this is the natural frequency of a LC circuit, or what we call the resonant frequency. So let's say we wanted to use this to keep track of time, like a clock. Then let's say that we had an L value that was equal to 1 millihenry, and a capacitance value that was equal to 1 microfarad. Then we would say that our omega value would be the square root of 1 over 10 to the minus 3 Henry times 10 to the minus 6 farads. Or that would be the square root of 10 to the minus 9. And the denominator, 1 over that, so that would be 10 to the 9. That would be a billion. Square root of a billion is, sorry, that's going to be 3.16 times 10 to the 4 radians per second. Or frequency would be omega over 2 pi, which would be this divided by 2 pi. That would be 5.04 kilohertz. So we can get this thing to oscillate at a certain rate. And so this is the natural frequency of this system. Now, if we included the fact that coils of wire would naturally tend to have a resistance in them, we would have a damped simple harmonic oscillator. And that would be just like this system, but eventually it would run out of energy as the energy leaves the system. But what you can do, and this is something that we'll show on Thursday, is that you can, say, have a variable capacitor in a circuit with a resistor and an inductor, and you can tune in a certain frequency, and so that's how you tune in your channel on the radio. Okay? So you find that natural frequency at which this system tends to resonate, and then you drive the system at that frequency with something that comes in from an antenna. So it naturally likes to vibrate at that frequency. Just like if you had a mass on a spring, you hit it at a certain rate, it vibrates a lot. If you hit it at the wrong rate, it doesn't vibrate very much. And so you can use this then as what's called a bandpass filter to zoom in on one particular frequency that you want to observe. And so that's what we're going to do for our final lecture, is look at different applications of the LRC circuit. And didn't have time to do our group quiz, but we'll save that for Thursday.
Is the group quiz going to be due with the final?
No, it'll be due on Thursday at the end of class.
Oh, on Thursday.